In this video, we're going to continue looking at the electrophilic addition to conjugated dienes like we did in the last video. In this video, we're going to step it up a notch and also focus on the energetics of the reaction, looking at ways that we can use what we refer to as thermodynamic versus kinetic control to help drive what product is favored in the reaction so that we don't necessarily get an even mixture of the 1,2 and 1,4 reaction products, but instead we can steer the reaction to favor one of those types of products over the other. So let's take a look at an example to go through this logic behind controlling a reaction thermodynamically versus kinetically. So to lay things out for explaining how we can steer the reaction toward the 1,2 product or the 1,4 product using thermodynamic versus kinetic control mechanisms in the reaction, what we are first going to do is write out just the general reaction mechanism. So in the first step of this process of taking buto-1,3-diene and reacting with one equivalent of HCl, we protonate, which is going to be true anytime we're reacting with an acid here. So take our buto-1,3-diene, reacting with HCl. We're going to do protonation, so that means we're going to take the pi electrons. The molecule is symmetrical, so it doesn't matter which set of pi electrons we take. We bring those pi electrons over to attack the proton. That forces the hydrogen-chlorine bond to break, leading us to chloride anion, as well as our carbocation intermediate, which we have our 4-carbon chain. Carbocation goes right here. It will always end up at the allylic position because the allylic position is going to be stabilized by resonance because the positive charge is not localized and stuck on just that one position, but instead there's a second resonance structure where we can take the pi bond, bring it over to here, so it'll be there in the second resonance structure, and the positive formal charge then is out here at carbon number 1. And then from there, in the second step of the mechanism, the nucleophile, that is the chloride anion, is going to attack the electrophilic carbocation. So to show that happening, we take each of our 2 resonance structures, taking the first resonance structure, the one up top right here that we drew. I just redrew it down here. Bring in the chloride anion, that is our nucleophile. Comes in. It is going to attack the carbocation, like so. And coming in right here, carbon-chlorine bond, we get this as our product there. And then the other route for this is to use the second resonance structure, the one I'm circling with my laser pointer here. So I'm going to go through an analogous process for that where I draw out that particular resonance structure, bring in the chloride anion, and then from there, the chloride anion comes in, attacks the carbocation to make a new carbon-chlorine bond, giving us our other product of this reaction where we will have a new carbon-chlorine bond right here at this position of our chain. So in both of these cases, the chlorine has formed a bond allylic to the alkene group, where by allylic we mean that we go from the alkene group one spot over, and it's that carbon one spot over from the alkene group, where you will see the chlorine having formed a bond. Classifying these 2 products, we can describe each as either the 1,2 or 1,4 addition product. It will always be the case that one of these products is the 1,2 product, the other is the 1,4 product. And remember, we determine that based on where the proton and the chlorine atom added relative to one another. So going back to the first step of the mechanism in this protonation, we see that the proton added at the right-hand terminal of the molecule here, because this was a CH2 group to start, and we made it into a CH3 group here. And so, therefore, the new hydrogen that we added was out here at this end where we'd put the third hydrogen in place. And that was true for both of these resonance structures, that in both, the place where we added the new hydrogen was out here. And so, in the top scenario, the newly added hydrogen was bonded to the carbon adjacent to the carbocation, where the carbocation is where the chlorine ultimately ends up. And so we describe that top case as the 1,2 addition product, because the hydrogen and the chlorine nucleophile added here and here on adjacent carbon atoms. The other product had better well be the 1,4 product, or we've done something wrong along the way here. And indeed, if we think about the location where we placed the new hydrogen out here at the end, relative to where the chlorine comes in and bonds, they're at positions 1 and 4 relative to one another, where if we say the hydrogen is bonded at carbon 1, 2, 3, 4. So we refer to that as the 1,4 addition product. Now, looking at these two products that we have created here, one of these two products is more stable than the other, based on the criteria that we learned a couple of videos ago about the stabilities of alkenes. Looking at the 1,2 product in this particular reaction, the 1,2 product is a less alkyl substituted alkene than the 1,4 product, because the 1,4 product has 2 alkyl branches coming off of it. The 1,2 product only has 1 alkyl branch. And so therefore, we would describe the 1,4 product as being the more stable product because it's more alkyl substituted, and those alkyl groups increase the stability of alkenes. We describe the more stable product in any reaction as being the so-called thermodynamic product. So the thermodynamic product of any reaction doesn't have to be this type of reaction. Just in general, the thermodynamic product is the product that is the most stable. And a lot of reactions just in general lead to one product, and they give, no matter what the reaction conditions are, they give just that one major product that corresponds to the product that has the highest stability, the most stable product. For example, when we were looking at Zaitsev's rule, back when we were doing elimination reactions, we were always headed for the most stable, most alkyl substituted so-called thermodynamic product. So the thermodynamic product, by definition, in a very general sense, is going to refer to the product that is the most stable product. And in the case of this reaction, the 1,4 product is our most stable, therefore thermodynamic product, because it is the most alkyl substituted. In addition to referring to a reaction giving a thermodynamically favorable product, there is another type of situation and product that we can talk about as well, which is referred to as the kinetic product. The kinetic product of a reaction is the product that forms the fastest. Because the term kinetics refers to speed, and so the kinetic product is the product that forms the fastest. So it is the first one to the finish line. And so in the case of the 1,2 versus 1,4 product, there are different factors at play for this particular reaction that cause the 1,2 product to form faster than the 1,4 product. Specifically, the 1,2 product forms faster because if we think about the intermediates and how easily or how most favorably they form, for the two intermediates, the two resonance structures here, the resonance structure on top here is the dominant resonance structure. Because it is a secondary carbocation, which is lower in energy, than a primary carbocation, which is higher in energy. So in other words, during the reaction pathway, during the mechanism, this resonance form is going to be the preferred dominant resonance form. It's going to be the resonance form that, if we were thinking about these two as a hybrid structure, the hybrid would look more closely similar to this dominant resonance form than the other. And so due to that fact that this is the lower energy of the two resonance forms, when we get through the pipeline here, the faster route is going to be the route that leads to the 1,2 product, because that corresponds to a lower energy intermediate. The lower energy intermediate can be achieved faster. And so the 1,2 product is the kinetic product of this reaction. On the other hand, though, the 1,4 product is ultimately more stable. So it's this discrepancy here where when you think about the stability of the intermediates, That's in contrast to the stability of the products. So at the intermediate stage, our most stable dominant resonance form at that stage leads to a product, an alkene product here, the 1,2 product, that is the less stable of the two final products, but it forms faster due to the fact that the intermediate has a lower energy. So with the observation of a so-called kinetic product and a thermodynamic product for this reaction, a product that forms faster, as well as a different product, a different constitutional isomer that is more stable, we can manipulate the control of this reaction in order to drive it toward one product versus another by altering things like temperature. So what happens is at a low temperature, something like freezer level temperatures, we could say minus 20 degrees Celsius, minus 80 degrees Celsius, etc. So if the temperatures are kept low, there is no opportunity for equilibrium to form in the reaction flask. And as a result, what happens is that the reaction heads through the pathway here, it takes its fastest route through, and then it is stuck at whatever product it arrives at because there's no reverse reaction, there's no equilibrium. So that's what's going to be the case at low temperatures, is that there's not enough thermal energy for an equilibrium to be achieved. And when there is no equilibrium, there's kinetic control of the reaction. And whatever product forms the fastest, initially straight through the reaction mechanism, the fastest forming product is the major product. On the other hand, if the temperature is elevated, so at higher temperatures, and generally when we say higher temperatures, we're talking about levels above room temperature. So if we're conducting this reaction, for example, under reflux, meaning that we are boiling it, what will happen is that due to the heat energy, the thermal energy provided to that reaction, an equilibrium can form. And when there's an equilibrium, the reaction will keep shuffling forward and reverse until the product reaches the low energy state final product. So an equilibrium at a higher temperature can form, and the most stable final product is going to be the major product. In many reactions, the kinetic product and the thermodynamic product are one and the same, that no matter what happens in terms of there being an equilibrium versus not an equilibrium, the product that forms the fastest is also the product that is the most stable. And so if the product that forms the fastest is also the most stable, then you can't control the outcome of the reaction by altering the temperature. But in cases like this where there's a conflict between one of the products being the product that forms the fastest and a different product being the one that's the most stable, you can adjust the temperature or the energy available in the system to enable a situation where there's no equilibrium, meaning that just the fastest product is the one that will form because the temperature is kept low, and so there's no chance for equilibrium to occur, versus keeping the temperature high, where you can get an equilibrium between forward and reverse reaction, and that will enable the reaction to go back and forth, forward and reverse, until the most stable possible final scenario, the most stable possible final product is accomplished. And this is going to be true for reactions where the 1,4 product and the 1,2 product have different stabilities, wherein one of the products is more alkyl substituted than the other, because that's what's going to result in one of them being more stable than the other. We can draw this out using an energetics plot, or a reaction coordinate as we call it, and I'm going to draw out that sort of scenario or the pathways that lead to these two products to further illustrate in a diagram or schematic what we've just been talking about here in words. So in this reaction coordinate that I'm going to draw out, we're going to map out the energetics leading to the 1,2 product versus the 1,4 product of this reaction. So I draw my X and Y axes here. On the x-axis of a reaction coordinate, we post the reaction progress. We also call that the reaction coordinate. And the energy of the reactants, intermediates, and products on the y-axis. We start with our initial starting material right here, whatever the energy of that is. And in the case of our initial starting material, that would be the energy of our organic starting material, which would be our dienes. So that's just the energy of our buta-1,3-diene product. To get to the first intermediate via this protonation reaction, there is always a energy maxima, referred to as the transition state, which is the point at which the bonds are being broken and made. So we have a relatively energy maxima. It drops back down a bit. But to get to this first intermediate, we are still going to be ultimately in the carbocation product here at a higher energy level than we were at the start because of the fact that we have those positive formal charges in there, creating instability in the system. So we get to here in our energy curve after we've passed that transition state. And what we would have here are two different carbocation intermediates that we can draw. We have resonance structure number 1 right here, as well as resonance structure number 2, and I'll abbreviate those with Roman numerals just for 1 and 2. And in our second one, we have our carbocation out here at the end. And so what will happen next is that these two resonance structures are going to have different energetics as they leave this step and head toward the final product of the reaction. So I'm going to highlight our first resonance structure in pink here, and I'll be illustrating its energy curve in pink. I'm going to highlight the other resonance structure in green and show its energetics in green. So due to the fact that the first resonance structure in pink is more stable than the second one in green, what's going to happen is that this first more stable resonance structure is going to have a lower transition state energy to get out of this intermediate stage and onto the product. And so I'm going to show in pink my energy curve leading to the product here, where we have a relatively low transition state. We come onward to the product here, like so. And so this path that we've shown in pink here would correspond to our product, where we bring in the chlorine atom right here as shown, because we took this carbocation, we brought in the chlorine right here, and so that's going to lead us to our product here. And this, if we look back at our initial description here, that was our 1,2 product. So I'm going to label that as the 1,2 product here. So the 1,2 product, we said, had a lower transition state energy here to get toward the final product than the other one in green, our second resonance structure, because the second resonance structure was less stable than the first. So therefore, our activation energy here, our transition state energy, is going to be higher to get that second resonance structure onward down the pathway. There's a higher activation energy to overcome here. And so coming along the rest of the way, though, when we get down to the product and we think about the energy of the product for the 1,2 situation versus the 1,4, we said the 1,4 product was ultimately more stable. So the final product here of the 1,4 situation is more stable, and that means that the final product here in green has lower energy. And so that lower energy product, the more alkyl substituted product, I'm going to draw out like so here, and I'm going to label that as the 1,4 pathway in that bright green color. So the 1,4 pathway has, in thinking about what would make it favorable versus unfavorable relative to the pink pathway, the green pathway has a higher transition state energy here at the intermediate because of the fact that the carbocation is unstable. If we can get past that, the final product here is really stable because it's more alkyl substituted. On the other hand, the pink intermediate has a low transition state here because of the fact that it's a relatively stable carbocation, but then at the end of the pathway, the 1,2 product is less alkyl substituted, so it's less stable than the 1,4 substituted product. So ultimately, the end of the path, this red line has a higher energy. It's less stable in the final situation. And so the way that we can control this is if we keep the temperature low, at low temperatures, there is no equilibrium. So whatever route is the fastest initial pathway through here, that is going to be what is stuck as the final product. There's no equilibrium, in other words, at the really low temperatures. And so following through the pathway here, starting through the reaction at low temperature, when we get to this point, if the temperature is low, this pathway is going to take the lowest energy route through, very, very favorably to take the lowest energy route through. That's going to be this red point here is the lower mountain to climb. That's going to be the favorable one for this low energy reaction with very little heat available. And so the product comes over to here, and there's going to be no equilibrium because there's not enough heat to send the reaction back in the other direction. And so at low temperatures, we're stuck with the 1,2 product. That is the fastest product to form here. On the other hand, in the event that there is ample energy due to additional heat, this reaction can reverse, going back to the drawing board, back to the beginning, or at least back to here. And then if there is sufficient heat energy, it can, in minority cases, climb over this larger energy barrier and get down to here. And what happens is once it gets down to here, there's such a huge barrier to go back in reverse due to this giant activation energy necessary to go back in the reverse direction that the product gets stuck here, and that becomes the major product. And so the difference here is that with this particular scenario, the intermediates of these reactions have different stabilities and are in conflict with the stabilities of the products. And so therefore, we have the opportunity to control the outcome of the reaction by using heat to supply the energy necessary to reach equilibrium, and ultimately equilibrium conditions are going to favor the most stable final product, whereas the kinetic control of keeping the temperature low allows only the fastest initial product to form because there's not enough energy for the reaction to be reversed, and so that would favor the 1,2 product. And so generally what you're looking for here is if you're in a situation where your final products of these diene addition reactions have different stabilities, if the reaction is done at elevated temperatures, meaning greater than room temperature, it's going to favor the 1,4 product. If it's done at low temperatures, it's instead going to favor the 1,2 product. If it's somewhere in between, like right at room temperature, quite possibly it could yield both. But if you want to steer it toward one or the other, you need to use either elevated temperatures or very low temperatures. And keep in mind, this only works in cases where the final products have different stabilities. If you'd created a 1,2 and 1,4 product that had similar stabilities because they were similarly alkyl substituted, you wouldn't be able to exert this control over the reaction.